Good morning and happy Halloween. Um, so let's talk a little bit about the quiz. There's going to be a quiz on Thursday. It's going to cover one of the first 7 problems on the homework. Yes. Yes. So there's. I just want to throw this out there in case there's any questions. I know originally I said I said like, oh, until the homework's due, I'm not going to have a quiz on it. So that policy is going to be modified a little bit because I started extending the homeworks and giving more time to do it because I don't want to take off points, and if it's late, you're still going to get full credit for the homework. So the rule with the quizzes is if we covered it like the last week and I finished lecturing over it, then the following week it's like fair game to be on a quiz. Basically like common sense. If I taught something and it's been like last week, then it's considered fair game. So the homework 3, I'm not going to say any problem off of it. I'm just going to say one of the first 7. And then obviously for the second midterm, anything that's on homework 3 is going to be fair game. But since we're taking our time, we're not rushing this material. The biggest problem with this course and the other course is that there's too much material in the span that they're recommending I teach. I can't teach it well if I teach all the material, so I have to slow the pace down a little bit. But I can't go too slow because it has to sort of correspond to what you're doing in your labs. I know you probably already did circuits, but that's okay because with the circuits, we are going to do circuits, but you're going to get most of that advanced circuitry with if you're a double E or an mechanical engineering major. You'll take another class in that where you'll go into the depth. Here we're going to talk more about the phenomena and what's really going on. That's more of the physics aspect of it. I don't focus on the circuit rules as much because it's very complicated. Some of these circuits are very, take several weeks to get good at that. And if I threw a bunch of hard circuit problems on an exam, it would just be kind of like a test of your sanity. Like, how fast can I learn these rules for this exam? So there is going to be some circuits. I'm not saying there's nothing, but I'm going to do less of that and more explanation of the physics behind it. Hence, we're talking more about what we're talking about today: induced electric fields, eddy currents, displacement current, and Maxwell's equations. This material is fascinating. You'll probably never see it again because it's stuff that they just brush over. It's more about applications later, like how does the device actually work. People aren't interested in what's really going on. But this is a physics class. This is the science of what's going on. So we are going to talk about it today. So let's get started. Any questions about the quiz on Thursday or anything else before I begin? No. Yes. Yeah, we're going to do last 20 minutes for the quiz. Yes. Okay, great. Yes. I'm sorry, you're going to have to speak up a little bit. You're in the back. The late homework policy is if you do your homework late, you get 100% of the homework credit for it. Okay? I don't care if it's 3 weeks late. If you get it done, you get full credit. Anybody who does all the problems in this class, and if it says you get a 60% on the homework, you actually get 100%. I'm not going to be taking points off for you trying stuff and making mistakes and trying to solve the problems. That's stupid. The only reason the homework is there is to give you practice. I'm not grading your ability on the practice. I want you to make mistakes, and I want you to actually do the problems. If I graded the homework like it was a test or something, then you just try to get the highest score possible, and you just copy it out of a solutions manual or something and wouldn't really learn it. So I know that it's better to give you that leeway of like, okay, I'm going to actually try to learn this. If I make a mistake, it's okay, because that's how learning actually occurs. And I want you to actually learn and enjoy the material. Yes. So that's my policy. You're going to get 100% credit for the homework. Obviously, it's better to do it sooner rather than later because there's also those quizzes that are based off of the homework. So you do need to get some of it done in a timely manner. You don't want to wait till the last minute for everything. But if there's a problem or two that you didn't get a chance to do, you're not going to lose points if that says late. The mastering grade does not correspond to your actual homework grade. Okay, any more questions about that before I begin? Okay. So, we've learned that Faraday's law is valid for two different situations. There's this one situation where we have an EMF induced by magnetic forces on charges when a conductor moves through a magnetic field. So we have this conductor. Sorry, there's a lot of text there, but there's a lot of little points that I need to make sure I don't forget to mention. So I got to put everything on there, lay it all out. Okay. We got a conductor moving through a field, okay? And that produces a induction situation. In the other situation, we've got a time-varying magnetic field that induces an electric field and hence an EMF. The E field is induced even when no conductor is present. This E field differs from an electrostatic field in an important way. It's non-conservative, so the line integral of E dl around a closed path is not zero. That's a kind of a little technical point about vector fields and stuff, which I'll sort of discuss here. So what does it mean when the line integral around, for a conservative field, what does it mean when a line integral around a closed path is zero? This is what it means. So if I have some sort of line integral, and remember we talked about the line integral being the value of the function along this path here, and I have some sort of conservative field, then for the conservative field, there's going to be parts going this way, but there's also going to be parts going this way. The line integral, the value of the field along this closed path. And these paths are all going to cancel out because one's going this way and one's going this way. So all these little differential bits for a conservative vector field, they're going to sum up to be zero. But that's not the case for a non-conservative vector field. So why is it that this electric field that's induced is not like a static electric field from a charge? Because a conservative vector field includes things like a collection of charges. That's going to produce a conservative vector field. Here we have non-conservative. So why is that? Well, first of all, when a charge moves around a closed path, the field does non-zero amount of work on it. So remember we talked about magnetic fields doing no work, but here we see that the field does do work on it, and it follows that for such a field the concept of potential has no meaning. So this idea of an electric or magnetic potential energy, that's an important concept. We use that so much in physics. Incredibly, that doesn't have any meaning in this scenario for an induced field. So that's pretty weird, because everything that we've learned in physics up to now, all the forces that we can describe, they've always been in terms of like the gradient of a potential. For example, your gravitational field, you've got your acceleration component of your gravitational field, ma equals F. Let's say it's force due to the gravitational field, right? It's like m big G over R squared, and there's like a minus sign there. Well, the force is the potential associated with this is the integral minus the integral of this. So we have that force can also be, for a conservative field, it can also be expressed as minus the gradient of the potential. So if I take the derivative of the potential associated with my gravitational field, then I get the force associated with it as well. So you can see that it's something like, it goes like mg over r. And you also can have the same analogous concept for electric potential. You have this 1 over r for an electric potential, and then it's minus 1 over r squared for the force associated with that. Now I'm going to erase that because that doesn't apply to what we're talking about today. But I just wanted to illustrate what we're talking about when I say that it can't be expressed in terms of a potential. and how that relates to what we did before. Because you've seen gravitational potential. You know that there's gravitational potential energy. So there's still energy in this field, but it's not electrostatic. It's not an electrostatic field. It's not a normal energy that can be phrased in terms of a potential. So it follows that for such a field, the concept of potential has no meaning. We call such a field a non-electrostatic field. In contrast, an electrostatic field is always conservative, and that was talked about last quarter for you. And it has an associated potential function, which I just talked about for the case of the gravitational potential. Okay. Despite this difference, the fundamental effect of any electric field is to exert a force F equals QE on a charge Q. This relationship is still valid whether E is conservative and produced by charges or non-conservative and produced by a changing magnetic flux. Okay, finally, what's the one thing I can think of just intuitively that could sort of lead a hint as to why this field is non-conservative, whereas my field, my QE associated with, say, a collection of charges is conservative. Let's think about permanence here. When I take a charge, okay, when I have an electric charge, that charge has some intrinsic property in nature due to it. It has, let's say, an electron. An electron has an intrinsic spin, a quantum number, that's associated with its angular momentum. It's quantized too. And it has a certain quantum unit of charge. Every electron has the same amount of charge. And when nature creates my electron, and it creates this little fundamental particle, an electron or a proton has the positive charge. Either way, when this thing is created, it's created in a form of mass energy. It has a mass associated with it as well. Every electron and every proton has the same amount of mass. And it's created and it's there. There's a permanence to it. In contrast to this field is produced by a change in flux. So there's a change in flux. There isn't sort of like this permanent mass energy created with a particle. And that's sort of one way you can see how there's a fundamental difference between this field, this electric field, versus the classic electrostatic field associated with charges. It's not created by a fundamental particle, it's created by a change in flux. But it's fascinating that for a moment you can actually get the same effect from a change in a field as you can from a fundamental particle. We can get the same units, the same force. It's just the origin of it is completely different. It's not exactly the same because it's non-conservative, but other than that, it is. Anyway, that's sort of an interesting thing to think about. So a changing magnetic field acts as a source of electric field of a sort that we cannot produce with any static charge distribution, because there's the fundamental difference of how it originates. They don't originate in the same way. What's more, you can see that a changing electric field acts as a source of magnetic field too. So the electric field can change and produce a magnetic field. So there's a symmetry between the two fields in electromagnetic waves, a symmetry that one of the most famous physicists of all time, Maxwell, discovered and used to great effect. And we'll talk about that more coming up. So you can consider a few practical applications. We have guitars. Electric guitars have pickups that use currents induced in coils by the vibration of ferromagnetic strings. So the strings are magnetic. This is how an electric guitar works. The strings are magnetic. The pickups, those little metal things in the neck of the guitar, not the neck, sorry, the little metal things that are below the neck. So you have like the guitar here, and then you have the body of it, and then down here you might have like some pickups. The string is gonna go down like this. There's like 6 of them in a guitar. And then when those strings vibrate, it produces a signal that the coils can pick up. It's a change in a magnetic field, which is a flux. And what happens is that change in flux from the strings vibrating, the pickups, the electric signal is so sensitive to that change that it actually produces an electric signal, and the electric signal is amplified through an amplifier, and then our ears can discern that difference. So depending upon how you strum the guitar, whether you play it really loud or you play different like style of strumming or different notes, all of those things are actually detected as field information. And now you can see how it happens. The pickups work through electromagnetic induction, because the change in the magnetic field from the strings produces an electric field, which can then go through to the signal and be amplified through the electric apparatus of the amp. It doesn't work, it does still produce a flux when it's not plugged in, but you don't hear the flux because it's not amplified. The signal's too small. There's nothing to amplify it into a significant sound wave through the speaker. The operation is pretty complicated, but it makes sense when you see electromagnetic induction. The alternator, which we talked about in the last class, in most cars uses a rotating magnet to induce currents in stationary coils. And whether we realize it or not, magnetically induced electric fields play this important role. So here's some applications. We have a car that's powered by an electric motor. As the car comes to a halt, the spinning wheels run the motor backwards, so it acts as a generator. This is kind of like Priuses work like this. So like if you have a hybrid, it also works like this. The hybrid gets started up and it gets its initial momentum from a gasoline engine, but then it uses this motion of the spinning wheels to use as a magnet, and the spinning wheels produce a changing magnetic field. So if you're driving a Prius or some kind of hybrid, when the car comes to a stop, you can actually, the wheels are still spinning, and that change produces a change in the magnetic field, which produces a current. And the current goes through to the lithium battery in the back seat of the car. There's a secondary battery that's like, not the main battery that you normally think about with the car battery. It has one of those too, but it also has the lithium battery. And that signal, that electric current, gets generated and goes through and actually charges the battery. Okay, so then we also have the rotating crankshaft of a piston engine airplane, and it spins a magnet, which induces an EMF in an adjacent coil and generates the spark that ignites fuel in the engine cylinders. And this keeps the engine running even if the airplane's other electrical systems fail. So you've ever heard of a backup generator in hospitals? Same concept here. Same concept as a backup generator. Even if we lose power, we have a source of electrical current in the case that we have a power failure, so that we don't lose everything. They're going to put something like that in a helicopter as well, because otherwise you have to worry about a crash happening. Okay, let's do an example. Suppose we have a solenoid that has 500 turns per meter and a cross-sectional area of 4 centimeters squared. The current in its windings is increasing at 100 amperes per second. So we've got an increase in current. Find the magnitude of the induced EMF in the wire loop outside the solenoid. Find the magnitude of the induced electric field within the loop if its radius is 2 centimeters. All right, pull out a sheet of paper and try to work that one, and then I'm going to work it out on the board. So this is an interesting situation. Now we've got a solenoid, and it's got 500 turns, and it's doing some sort of thing because we've got an increasing current. But it's not a magnetic field now. It's not a changing field. It's a changing current. And it's saying, what's the induced EMF in the wire loop outside the solenoid from this change in current? Okay, so let me draw like a little bit of a picture of this here so we can see this better. So you've got this cylinder here going out into space like this. And then we've got these windings. So let's draw these in purple here. So we've got coming around like this. Okay, there's the windings of the solenoid. And then we've got a galvanometer, which is going to be our detector for the current. We use a galvanometer for that. So we'll draw that out here. Get out a sheet of paper and try to follow along with this. It's really helpful to draw pictures of this while you're thinking about what's going on. Okay. Sorry, it's a little bit kind of a lot going on here, but try to erase this. So this is my galvanometer in pink. The coil of the solenoid is in purple. I've got some changing B field because I've got some current. So the blue, it says here, the blue cylinder shows the region where there's a magnetic field. So everywhere inside this solenoid, what this cylinder represents is actually the existence of a B field within this. And if you remember from your exam that you had, I had a question on there about a solenoid and the magnetic field. It's essentially zero outside of a solenoid. So the B field is all inside here. B field like that. And then, and it's going this way, okay? And so we've got this interesting result here. Now let's see what we've got current. But oh yeah, I didn't quite complete this, did I? I gotta also describe where's the current coming from. I is coming from this direction, and it's got a changing current, di by dt. I shouldn't put a vector over that. It's not a vector. Okay, so we've got a current, and we've got a change in current with respect to time. We've got our current, and it's going around this, and it's actually going to induce a current in the galvanometer. So there's going to be a current here too, an I prime. There's a current induced in the wire of the galvanometer, and there has to be, or else the galvanometer wouldn't detect anything, because the galvanometer is not connected to the wire loop of the solenoid, is it? No. So if there was no wire loop there, the galvanometer wouldn't detect anything, but there is. Okay, so the increasing magnetic field inside the solenoid causes a change in the magnetic flux through the wire loop, and hence induces an electric field E around the loop. Why is there a change in the magnetic flux through the wire loop? Why is there a change? Real quick, somebody. Anybody, raise a hand. Why is there a change in the magnetic flux? Yes. Yes, perfect. Change in current. The current is changing, and we know that the current generates a magnetic field by the right-hand rule. So a change in current should generate a change in magnetic field. Sometimes physics is not at all intuitive, but this one perfectly is. Perfectly intuitive. Great. So we have a change in B field. Okay, so this is going to induce an electric field now around the loop. And then we're trying to find the induced EMF and the electric field magnitude. So we can use equation 29.8 to determine the EMF. The loop and the solenoid share the same central axis. So by symmetry, the electric field is going to be tangent to the loop and has the same magnitude E all the way around its circumference. So we can use 29.9 to find the electric field. And if that last part you're kind of scratching your head a little bit, that's okay. This is not super simple. That's why a lot of people skip this over, because there's a lot of geometry going on here, but it's very fascinating. It's very important. So we use our equation to find the induced EMF. And we have our formula for the B field. That's where, of the solenoid. That's where that formula comes from. So we've got our B field of a solenoid, right? We remember that from the exam. We could use that on our exam to give the B field of the solenoid. And now we have a change in current. So we've got this change in EMF minus dB by dt. And that's going to be equal to minus, this is associated with the magnetic field of the solenoid, number of turns times the area, and then we have our current, di by dt. So you can see there that the current term is what takes on the time dependence there. So we plug in those values, and we've got like our permeability of free space, minus 4 pi times 10 to the minus 7 Webers per ampere times meters. So minus 4 pi times 10 to the minus 7. We'll do units, Webers per ampere. It's nice to have our units written out there. And then we've got 500 turns, okay, per meter. So we're going to do turns per meter. There's still a little bit of a unit there. 4 times 10 to the minus 4 for the area. This is the area that's coming in here. 4 times 10 to the minus 4. And that's going to be meters squared. Perfect. Units of area. Finally, we've got our current, which is 100. Change in current, which is 100 amperes per second. It's a change in current. So it's almost like an acceleration. Almost. We won't say it's an acceleration, but it's kind of like an acceleration. Okay, that gives minus 25 times 10 to the minus 6 Webers per second, which has units of volts. Minus 25 times 10 to the minus 6 of volts. Sorry I ran out of space here on the board, but you get the idea. We've got a voltage here, and 25 microvolts, minus 25. By symmetry, the line integral of E dot dl has an absolute value 2 pi r e, no matter which direction we integrate around the loop. This is equal to the absolute value of the EMF. So here we have that the electric field is equal to the average value, or the absolute value, sorry, not average, absolute value of the EMF. So we have our EMF. Now we say the absolute value of this is all that matters. That divided by the line integral of 2 pi r, which is around the loop. So we have, what am I talking about when I say 2 pi r? I'm talking about a section of the loop. 2 pi r is this r. So I have a radius here in r of this loop, the area of this loop. So there's a change in flux around this loop. The solenoid has a changing magnetic field. The solenoid is going through the loop with the galvanometer. The change in flux associated with this change in current and changing magnetic field drives an EMF, and it's going, you can see the current is driven this way, so the EMF is going this way as well. We have a B field, and there's also going to be a B field to oppose this current. To oppose this, or I mean not to oppose the current, to oppose this change in flux. And we know which way the B field is going because we know that we have an increasing B field. So we know that the B field has to be opposing that increase, going the opposite sense from this loop. And then here what we're talking about is we're saying that we can actually find the electric field. The electric field, which is not the same thing as the EMF. The electric field is the same thing, not the same thing, but similar, the same idea as the electric field associated with charges or a battery or something like that. The electric field, E, associated with this change in flux is the absolute value of the EMF that we found from this step divided by the total line integral of 2 pi r. So the total value of the field all the way that lies along this line, we can do a line integral there, and that's our electric field. And when we do that, we look at the value of the EMF. The absolute value is 25 times 10 to the minus 6. We don't care about sign anymore. We're just looking at absolute value. And then our total line integral around this whole loop is 2 pi r. So the total value of this, yes. Okay. So we have that a changing magnetic flux through a closed loop produces an induced electric field. The line integral of E around the loop is equal to the induced EMF in the loop. So if we know the induced EMF and we know the line integral, then we know the electric field. So we have to go, so finding this electric field is not a simple matter. I mean, it kind of is, because we could look at the reading on the galvanometer actually, and we could infer an electric field based off of that too. But if you want to be technical about it, the technical way to find it without using just like a measuring device analytically through math is by this formula. We know what the EMF is, and then it's going to be the line integral of E around the loop is equal to the induced EMF. So we can find E per unit length. It's essentially what we're doing here. See? And you can see that. The electric field, it's going to be, the units of the electric field are actually voltage per unit length, which is interesting because we don't normally think of an electric field in terms of those units. Usually we think of the electric field in like coulombs or something like that. But you can see actually it's in voltage per unit length, because we have EMF here, voltage per unit length. It's pretty interesting. Okay, now we're going to talk about eddy currents. This is going to be important for Thursday because I'm going to do a demo on Thursday of some really cool stuff involving eddy currents, and we're also going to talk about displacement currents too. So, in the examples of the induction effects that we've studied, the induced currents have been confined to well-defined paths in conductors and other components forming a circuit. However, many pieces of electrical equipment contain masses of metal moving in magnetic fields or located in changing magnetic fields. In situations like these, we can have induced currents that circulate throughout the volume of the material. Because their flow patterns resemble swirling eddies in a river, we call these eddy currents. And this has to do with the curl of a magnetic field. Remember that cross product I was telling you about with that curl? And it's like, okay, we didn't technically talk about the curl yet. The curl is the derivative involving a cross product. We will talk about that. But I haven't introduced it yet because I didn't need it for anything, and I don't believe in introducing math until we use it for this class, because it's a physics class, not a math class. Anyway, the point is that we can have this property of a field of the curl, and it's the gradient crossed with the field, del cross B, for example, or del cross E. And we have the curl of the electric field, del cross E, the curl of the B field, del cross B. Let me put this out on the board really quick. So we have like a curl, which is like a gradient crossed with some general field. And we call this the curl of F. The point is that this measures the amount of rotation I have in my field. So if I have some field and it has a rotation in it, it's got a curl. So an electric field does not have a curl, because an electric field, if I look at the direction of an electric field, it's straight out. Like whether it's a positive or a negative charge, it's just going outward. There's no curl associated with that. Meanwhile, if I have a magnetic field from north to south, there is a curl associated with that because we have different directions. So curl and no curl. For the electric field, no curl. For the B field, yes, there is a curl. So now we can see this happening in the flow pattern of the eddy current. So what's actually going on here is that the induced current can go anywhere that it wants to. It's no longer confined to a wire. That's the critical point I want to drive home here. We're always used to thinking of currents being in wires. And I'm going to ask people to sort of hold off on the talking until discussion or office hours, just because it's a little distracting. But I promise you'll have plenty of time to talk about this more. I know this is a very fascinating subject, and there's a lot to grasp here. So it makes sense if you have questions. And actually, I'll encourage people, if they have questions right now, they can raise their hand, and I can address those. Anybody have any questions? Okay, great. So we have these currents that are not confined to wires. We can have a metal conductor, and the current can go anywhere at once. But it doesn't just go anywhere at once. It has a current. It follows a pattern, and it's a circular pattern. And it looks like a swirling eddy in a river. So, as an example, consider a metallic disc rotating in a magnetic field perpendicular to the plane of the disc, but confined to a limited portion of the disc's area, as shown in this figure here. So let's draw this figure out so we can see exactly what's going on here. Okay. So we've got this disc, this circular disc like this. Okay. Now, this disc has an eddy current, and there's a rotation associated with this disc here. So like an omega, a rotation. And it's rotating in a magnetic field perpendicular to the plane of the disc. You can barely see this in this drawing because they have it in a color, but the B field is into the page. So there's a B field, it's everywhere into the page here. That's my B field here, into. And we've got this eddy current that's associated with it. So we take a slice of this pie here, associated with this disc. We've got a couple of pie slices here. And then we've got, like, we label them like A and C. And then there's another slice. Actually, I'll call this slice B here. And then we've got another slice over here of this pie. We'll call this slice C. So we put these slices, and you know what? Let me put this magnetic field in a different color. Let's make this magnetic field nice and blue here, so we can differentiate between all the lines going on. And let's make this rotation pink, so we can see everything that's going on in our little picture here. Okay, so now we've got some eddy currents, and the eddy currents are wrapping around this situation, this disc, and they're following closed paths here, like this. Okay, we've got lines here, got another one here. Okay, and this is all throughout this volume. But since the charges tend to accumulate on the surface, even of a conductor, probably there's a lot more of it on the surface. But it's not restricted to like a wire or something. It's going all the way around. Okay? And then we've got even more going on in this picture. We've got some sort of force they've drawn here. Force, F. So, there's a B field, and it's perpendicular to the plane of the disc going into the page. B is going in. But confined to a limited portion of the disc's area. Okay, so that's what's going on with these slices then. We've got, oops, sorry. Wrong slide. Okay. So we've got, it's confined to a limited portion of the disc's area. Sector OB is moving across the field and has an EMF induced in it. So this section here, B here, is moving across this field. We'll sort of illustrate that I'm talking about this portion of the disc here. It's moving across the field and it has an induced EMF in it because there's a change. Okay, I'm just going to close this one out. Okay. And it has EMF in it, and then we have sectors OA here, this one and this one, that also have an induced, they're not in the field, but they provide conducting paths for charges displaced along OB. And they return from B to the origin. So the result is a circulation of eddy currents in the disk, sketched here. Okay, so we have an eddy current that's generated. What's actually going on? The sector is moving across the field and it has an induced EMF in it. OA and OC are not in the field. So the magnetic field is actually limited to this region here. So I'll change this around a little bit. We're going to say it's only going in this area here. So there's no magnetic field everywhere. It's just in this sector here. And then what happens is we can draw the region where there is the magnetic field. So the B field is into the page, but it's only in this region. So then what happens is that OA and OC, they're not in the field. They're not part of this, but they provide return conducting paths for the charges displaced along OB to return from B to O. So the result is that we have a circulation of eddy currents because the current is starting, and I should draw this too. So we have currents originating in this B field here, and then they're circulating around because they originate in a portion of this B field. And notice they're going in opposite directions for different sides of the disk. They're not all going in the same direction, but they're going in directions that are consistent with our rule for the induced EMF of a B field, which we talked about. So depending upon which side of this, the current is going in a different direction. See, here the current is going this way, here the current is going this way, so we know the EMF has to be going in two different directions as well. So this is a very fascinating situation here. So the metal disc is rotating through this magnetic field. The resulting eddy current produces a braking force. And what is this braking force? I've sketched it here, F. We can use Lenz's law to decide on the direction of the induced current in the neighborhood of sector OB. Remember, I just mentioned this. The currents are going in different directions. We can use Lenz's law to confirm that they're going in different directions because the current must experience a magnetic force. So F has a magnitude here, and it has a direction too. We have IL cross B. That's the magnetic force. L is a vector, B is a vector. Force is IL cross B that opposes the rotation of this disk. So remember we had the slide wire generator, and I talked about how the field is actually interacting with the mechanics of your hand. Same idea here, kind of. We've got this mechanical system that's rotating, and then we have this current that experiences a magnetic force that opposes the rotation of the disk. And so this force must be to the right because the disk is rotating, so it's going this way, and the force is like trying to push it back this way by going like this, perpendicular to the axis of rotation. It's like sort of like going to induce a reverse torque. There's a torque associated with this rotation because we have a rotation about an axis, and then we have a force times a lever arm going this way that can stop that rotation, called a braking force. Okay, so B is directed into the plane of the disk, and the current and hence L have downward components. The return currents lie outside the field. These are the return currents. They lie outside the field, so they do not experience magnetic forces. The interaction between the eddy currents and the field causing a braking action on the disk. It causes that. And these effects can be used to stop the rotation of a circular saw, for example, when the power is turned off. So we can use eddy currents as a braking device. They could be used in electric cars too. You can create a braking force that stops a rotation. And we can also use it in electromagnets. They can be mounted in the cars to induce eddy currents in the rails of a rapid transit vehicle. So like monorails and things like that use these eddy currents as a braking device. The resulting magnetic fields cause the braking forces on electromagnets and thus on the cars. So here's another example of some applications. So we have a metal detector at the airport. We all hate going through airport security, dealing with this. You know how you go in that box and you do this thing with your arms, right? Now we can see why. So we've got this metal detector that generates an alternating magnetic field, B0. This induces eddy currents in a conducting object carried through the detector. So if I have a gun or something that a gun is a conductor, the gun is going to have an eddy current and we're going to detect that gun, or a knife. And the airport security is going to see it that way. So I can't sneak by security with a gun. I have to use a 3D printer to make one out of plastic or something. Okay, won't get into that. But anyway, okay. So if I'm doing my other job, my side job as a assassin for James Bond films, whatever. Okay, so it induces an eddy current in the conducting object. The eddy currents in turn produce an alternating magnetic field, which induces a current in the detector's receiver coil. So there's an induced current going on here that the receiver coil can detect. So there's a double process here. So the eddy current is generated by an alternating magnetic field, and the eddy current itself produces another alternating magnetic field. Why? Because since the B field is alternating, the current must be alternating too. It's not a constant source of current, so it also produces a changing magnetic field, not a constant magnetic field, which can be picked up in the receiver coil. And then metal detectors work on the same basic principle as well. So we have a metal detector that has a pulse of current traveling through it, and then it detects the eddy currents of a valuable gold bar at some beach in Spain where a ship wrecked in the 1600s. Somebody finds some gold bar on the beach and becomes an instant millionaire because they detected the eddy current in the gold bar, the metal object. Gold's a great conductor, so is silver. So we've got these wonderful, valuable conducting metals. And how do we find them? Eddy currents. Because what happens is the eddy current sends, when we put the metal detector up to the ground, the metal detector has a changing magnetic field through a pulse of current. Why does a pulse of current produce a changing magnetic field? Because a pulse of current, just a jolt of it, is not constant in time. It has a finite length. So it's not a steady current. Remember, in all of our problems with constant magnetic fields, we always talked about steady currents. Not a steady current. It's a pulse of current. It only acts for an instant. Thus, it has a changing magnetic field. Thus, it induces an eddy current in the solid conducting metal. The solid conducting metal then produces its own B field. And then this metal detector actually detects the B field. So all of the time, you're like, how does this metal detector work? Beep, beep, beep. That's pretty weird. It knows there's metal there, even though it's not making contact with it. It's making contact with it through a field interaction, a non-contact B field interaction. And now you know how it's detecting that B field. Because a changing B field does what? A changing B field induces a current. So when this eddy current in this gold bar produces this changing magnetic field, there's a sensitive coil that detects that, and it produces a current. And the current is used to give information. Every piece of information device that we use involves current, like this laptop, whatever, you name it. The current tells us, hey, there's an object there. Very important. Okay, so there's more uses, and we can talk about that, but so there's also undesirable effects associated with eddy currents. In an alternating current transformer, coils wrapped around an iron core carry a sinusoidally varying current. The resulting eddy currents in the core waste energy through I²R heating and set up an unwanted opposing EMF in the coils. So we have to minimize these effects to have a core that's designed so that the paths for the eddy currents are as narrow as possible. And we can talk about this more when we talk about transformers and circuits. Okay, one last cool example of eddy currents. You know I'm going to love this being from the astrophysics, okay? So Io is this extremely volcanic moon that orbits around Jupiter. We remember Jupiter from our exam, right? Yeah, pretty cool. Maybe making another appearance, we'll see. Okay, so Jupiter's moon Io is slightly larger than Earth's moon. It's bigger than Earth's moon, and it moves at more than 60,000 kilometers per hour through Jupiter's intense magnetic field. It's about 10 times stronger than Earth's field. The magnetic field is 10 times stronger, but because the area of Jupiter is so much bigger, the magnetic dipole is like 20,000 times bigger than Earth's magnetic dipole. So the dipole also plays a role. But anyway, this sets up strong eddy currents within Io. Where do these eddy currents come from within Io, though? Well, the crust might be a little bit magnetic on Io, but we can almost be certain that the majority of this comes from its core, because it has an iron core. Most of our terrestrial moons and our planets, like Earth, Venus, Mars, they have like metallic cores. Io has a metallic core. There's eddy currents that are circulating in this metallic core, producing intense amounts of energy that's dissipated that heats Io's interior. So that's why it comes from the interior, because the core is heating, and it comes up and it causes these massive volcanic eruptions on the surface, as shown in this close-up image. This is an actual image of volcanic eruptions on Io. It's absolutely scorched. This place looks like hell on earth. There's huge volcanoes everywhere. It's all because of the magnetic fields of Jupiter and its proximity to Jupiter, caused by these eddy currents from these induced currents within the core. Because currents carry a lot of heat and they dissipate through resistance. Remember, V equals IR, and we've got this heat associated with the current that heats up the core a lot. Okay, let's take a break, and then when we come back from break, we're going to talk about displacement current and Maxwell's equations. Okay, let's get started now. So we've seen that a varying magnetic field gives rise to an induced electric field. In one of the more remarkable examples of the symmetry of nature, we've got that a varying electric field gives rise to a magnetic field. So if we have a varying electric field, an electric field that is not constant, we're always going to have a magnetic field as well. This was discovered by Ørsted, I believe, in a lab. He was playing around with magnets, and he changed the electric signal, and he noticed that there was a change to his magnets. And Faraday also worked on this as well. This effect is of tremendous importance. It explains how we have light. So, we need to generalize Ampere's law, which we saw. Ampere's law was this convenient little, it looked like a cute little trick for finding the magnetic field for currents or whatever in the last class. But now we're going to see why it's such an epic equation and why it's so important. And it's because we have this relationship between electric and magnetic fields that we can see in Ampere's law. Remember, line integral of B dot dl is equal to mu naught over I enclosed. So the line integral of the B field is equal to like the current that's being enclosed. So if I have a couple of currents going into the board from some wires going this way, and then I draw a thing here, I've got this line integral around here. We've got like a line integral of B dot dl, where I'm summing up. The dot product means I'm summing up all the components of the B field that are going to be, and which my B field, right hand rule, okay, tells me the direction of the B field. The B field's got values all along this path. And if I make the path smaller, this still works, because what happens is, by a beautiful consequence of nature and geometry, If I make this path smaller, this B.dl, we could call this B.dl1, B.dl, B1 dl1. This is equal to B2.dl2. These two line integrals are equal, even though they're different paths and they have different dl's associated with them. The dl is not the same. The B.dl is the same. Why is the dl not the same? Well, obviously this is a bigger line, so this is a longer path than this one. But what happens is the B field grows in strength in exactly proportion to the change in the fall off with like length of the path integral. And it doesn't even matter what path it is, as long as it's a closed path, it can be any shape we want. How cool is that? That's amazing. That's why this thing is so cool, because it's maybe not very complicated and it's easy to solve problems, but that's why it's so cool, because it makes things so easy. Well, okay, but we have to do something with it. There's a problem. Ampere's law in this form is incomplete. And the process of charging a capacitor, we can see that. We've got these conducting wires that lead a current I capacitor into one plate and out of the other. The charge increases on the plates of these capacitors. So we have some capacitor here, and charge accumulates on one of the capacitors. And so we have an increasing voltage across the plates of this capacitor. Okay? And IC indicates that it's a conduction current, and that distinguishes it from a different kind called a displacement current. We use lowercase i's and v's to denote the instantaneous values of currents and potential differences, respectively, that vary with time. Okay, so let's talk about this a little more. Okay, so we've got a parallel plate capacitor being charged. Let me draw a better drawing of this now. So first of all, let me reverse it. It doesn't really matter, but since I'm going to keep inconsistency with the drawing here, we'll have these plates, and we'll make them cylinders, even though it doesn't actually really matter. Not cylinders, discs. So it's a parallel plate capacitor, but it's like a disc type of parallel plate capacitor. Doesn't have to be, though. It could be squares as well. Okay, so I've got these two discs. These are sides of my parallel plate capacitor. Charges accumulate, and there's an electric field between these charges, these charged up plates. And you remember, you charge the capacitor, and what happens to the value of the field? It gets stronger. The electric field grows as you separate these charges, and you produce this electric field. Now we also have a little bit of geometry here. So now we can see why they drew it as a circle, because it fits nicely in this geometrical picture here. So now I've got this volume here, and this volume is associated with this dl. So now you can see I'm going to use this to relate this to Ampere's law. So we've got a dl, and then I've got this current going in, this IC. So current's going in, and it's going all the way to E. Okay, so here's my current, IC. And we've got our dl here. This is the path that we're going to go for Ampere's law. And then we've got this surface, and we've got this plane of the surface here. Plane of the surface. Okay, the capacitor is being charged, and then the current IC is going through here, and then it's going out this way as well. Okay, so the conduction current through the plane surface is IC, but there is no conduction current through the surface that bulges out to pass between the plates. So the two surfaces have a common boundary, so this difference is in I enclosed and leads to an apparent contradiction in applying Ampere's law. So there's a problem with Ampere's law in this situation. because we found a little loophole here. We enclosed the path, and yet we don't have IC going through here. There's IC. You see how it ends right here? There's no IC right here. So there is no conduction current through the surface that bulges out to pass between the plates. So the conduction current dies off and then it goes again on the other side. So how do we deal with this? We need to apply Ampere's law to the circular path. The integral of B dl around this path equals mu naught I enclosed. For the plane circular area bounded by the circle, I enclosed is just the current IC in the left of the conductor, okay? But the surface that bulges out to the right is bounded by the same circle, and the current through that surface is 0. So, line integral of B dot dl is equal to mu naught IC, and at the same time it is equal to 0, showing a contradiction. But there's something else happening on this bulged out surface. As the capacitor charges, the electric field E and the electric flux through the surface are increasing. So there's a change in flux through this surface because it's charging and the E field is increasing. And the electric field is also increasing through the surface. So we can determine their rates of change in terms of charge and current because the units are the same. So the instantaneous charge Q is CV, where C is the capacitance of the capacitor. And V is the instantaneous potential difference. So not a velocity, a voltage. Potential difference is voltage. So Q is equal to CV, voltage. I would like a big V better than little v. Whatever. For a parallel plate capacitor, the capacitance is also equal to E naught, where E naught is the permittivity of free space from an electric field, times A over D, where A is the plate area and D is the spacing. So we have this potential difference between the plates, and that's given by the electric field times the distance, where the E is the electric field magnitude between the plates, right here. E is that. Okay. And we ignore fringing, and fringing is just things that happen outside the plate, small effects. We ignore that. And we assume E is uniform in the region between the plates. It's constant. So if this region is filled with a material with permittivity E, we replace epsilon naught, which is the permittivity of free space, with epsilon, which is the permittivity associated with this. So now we're going to move from E naught, which is like a constant associated with free space. You could think of it as like mu naught for a magnetic field. It's for electric field. We replace it with this epsilon for the capacitor. It changes. So now we've seen an intrinsic relationship between like the fundamental of nature. It changes a little bit when we have capacitors. Okay, so we substitute this into the expression for capacitance and voltage, and we can express the capacitor charge Q in terms of the electric flux through the surface. So now we have the charge Q is equal to the capacitance times the voltage, which is equal to epsilon, not epsilon naught, but epsilon times the area over D times the voltage, which is the electric field, times the distance separating them. And so then we have some things simplifying. We have this just turns into EA because the D's cancel. And so we have epsilon EA, and we know that E times area is just phi E. So as the capacitor charges, the rate of change of the Q is the conduction current. Taking the derivative with respect to time, we get that we have the IC here is equal to dq by dt, which is the change of charge with respect to time. We're familiar with that expression, but now we have this new expression, E times d phi E by dt, which is the electric flux through the surface. Phi E is a flux. So the change in electric flux times the permittivity through the capacitance region of this volume is my current. So the ability to support the current involves the permittivity of the capacitor and its changing electric flux. That gives me the current supported through this. And then we invent this fictitious displacement current, ID, in the region between the plates. So we say, okay, there's an imaginary current that connects them. So let's say, okay, you know what? There isn't really a current here, but let's say there is. Let's call it ID. What would happen if there was a displacement current in this region? Well, we have an expression for what the current would be from the capacitor. We just talked about it. It's going to be epsilon times the change in flux of the electric field. So that's going to be our current here. Not our IC, but our ID, displacement current. So there's an imaginary displacement current given by epsilon here times the change in electric flux with respect to time. Electric flux due to this electric field. And it's a changing electric field. Okay. Time rate of change of electric flux through the area. I want to stress that the entire time this process is occurring, this capacitor is charging. That's why there's a change in the electric field. Does everybody understand what's going on here right now? Yes. Okay, great. So, we imagine that the changing flux through the curved, bulged out surface is equivalent in Ampere's law to a conduction current through that surface. We include this fictitious current along with the real conduction current in Ampere's law. So now that I have this current going through here, I also have this fictitious current, displacement current, and then I change Ampere's law to involve that. So now it's not just B dot dl equals mu naught IC, it's B dot dl, line integral of that equals mu naught IC. So line integral of B dot dl equals mu naught, and then we have our IC plus displacement current. And then that's going to be what's enclosed by our surface. Because our surface incorporates this current going to the plate of the capacitor, which we know exists. So that's our first contribution. So we've got this bulged out surface, and right here at this surface here, on one hand, we have IC stopping here and going through here, and then right at this boundary, we have ID. So there's a changing flux due to both of these, because we have current going in and current going out. This one's going in, this one's going out. So we add these two together, and they're enclosed within this surface here. And remember, these are the plates of the parallel plate capacitor, and this is the electric field in there. Okay, so now we have mu naught IC plus ID enclosed. Ampere's law in this form is obeyed no matter what surface we use. So for a flat surface, if it's flat, if this is not curved here, ID is 0. For the curved surface, IC is 0, and IC for the flat surface equals ID for the curved surface. So this equation remains valid in magnetic materials, provided that the magnetization is proportional to the external field. So this was invented by Maxwell, who was working with Ampere's law, and he was trying to figure out a way to make it work. He made up this displacement current, JD, is equal to I displacement over the area. Using the flux, the electric flux is E times A, and we divide by this to find A, we find that this displacement current, JD, is equal to the permittivity of the capacitor times the change in the electric field with respect to time. And it makes Ampere's law work. That's the only reason he did it. He had no measuring device that could measure it. He just inferred that if this existed, we'd actually have Ampere's law would work. But it allows us to also generalize a junction rule from circuits. So if we consider the left plate of the capacitor, we have a conduction current into it, but none out of it. But when we include the displacement current going through here, we actually have conduction current coming in one side and an equal displacement current coming out. So this preserves the conservation of current, also known as the junction rule. Current in equals current out. So this situation without displacement current, this also violates Kirchhoff's laws. That's another important point about this. It's not just Ampere's law that gets violated, also Kirchhoff's. But this brings it back and allows for the junction rule where one current in through one junction equals current out the other. So we can think of this as a junction in a circuit, analogous to a junction in a circuit. Okay? And with this meaning of current, we can speak of current going through a capacitor. So we don't normally think of current. We say, what's the current through this capacitor? It's zero. Currents, that's what makes it a capacitor to begin with, right? There's charges here. If there was a current, actual current going through the capacitor would lose its charge because the current would no longer be accumulating on both plates. So that's how weird this displacement current is. There's no way it could be real, right? Because if there was, the capacitor would lose its charge if charge was accumulating. Assuming that the charge accumulated in this direction, but maybe it doesn't. We're still have to think about this a little more to understand that. Okay, so you can ask whether the displacement current has any real physical significance or whether it's just there to make the math of Ampere's law and Kirchhoff's work. So here's a fundamental experiment that helps answer the question. We can take a plain circular area between the capacitor plates, and if the displacement current really plays the role in Ampere's law that we've claimed, then there should be a magnetic field in the region between the plates. There should be a B field here as well when the capacitor is charging, because then there's a change in electric field while it's charging, so there should be a magnetic field there as well. And we can use the generalized Ampere's law, including the displacement current, to predict where the field should be. So now we're just looking at this region here in between these two plates. So we've got this region here between these two plates here, and then we draw this little line circle here to look at what's going on inside here, and then we call this point here A, and this point here on this circle B, and then there's a radius R associated with this little circle for this little path, and we call this we look at the situation and we say, okay, there's an electric field and a B field there at the same time. How does that work? Well, we've got a capacitor charging the current, and it has a displacement current equal to IC between the plates. With the displacement current density being J, D being the displacement current density, we've got this epsilon times dE by dt. This can be regarded as the source of the magnetic field between the plates. So this change, this displacement current is the source of the magnetic field, and it's going around this way by the right-hand rule. It still obeys the right-hand rule too. Got a B field going around here from this displacement current. Okay? So the capacitor has a displacement current equal to the IC between the plates with displacement current density JD. And why is it equal to IC? Because it has to be conservation of current. The junction rule, we say Kirchhoff's law generalizes. It has to. So let's picture these round capacitor plates with radius R. To find the magnetic field at a point in the region between the plates at a distance R from the axis, we apply Ampere's law to a circle of radius R passing through the point with little r less than big R. The circle passes through points A and B. The total current enclosed by the circle is the displacement current times its area. So we have I displacement over pi big R squared. times pi r squared. And then this integral b dot dl is equal to 2 pi r b, and that's equal to mu naught times little r squared over big R squared. So the ratio of those two r's times the initial current, the IC, and that gives us a B field here that's going to be equal to, so B field that's induced here in this region is mu naught over 2 pi little r over big R squared, because we had an R cancel, one of the little r's canceled there, times IC. So it's proportional to the initial current coming in. This result predicts that in the region between the plates, B is 0 at the axis and increases linearly. So the B field is not constant between this parallel plate capacitor, even though the E field is. That's really interesting. Think about that for a minute. Whoa, we've got a B field that increases linearly with distance from the axis. And similarly, outside the region between the plates, B is the same as though it were a wire and were continuous and the plates were not present at all. So outside of this region, it's like these plates don't even exist and there's a current that just goes continuously if we look at the B field induced from this. So geometrically, we're seeing a very different picture than what we're actually doing here. We're doing something very interesting with the fields. When we measure the magnetic field in this region, we find that it really is there. So there is a magnetic field there. Well, if there's a magnetic field there, then there kind of has to be a current. But that's crazy. So this confirms that the displacement current is a source of magnetic field. Even though it's not necessarily there, it's actually a fundamental fact of nature. It kind of is there. So this is the kinds of things in physics that we love. Because if we find something like this that says our laws of physics say this isn't possible, but then it is possible, then we know we've discovered new physics. And that's what we want to do, right? Like, if we want to advance as a species and explore nature, we're never going to get anywhere with the technology that we have now for space exploration. We're going to have to discover something like this, except we're going to have to discover it for quantum field theory instead. But in the 1800s, they discovered this for electric and magnetic fields, and guess what this led to? Cell phones, okay? Devices that generate electromagnetic waves for information, because this led to the realization that electric and magnetic fields are light. So with this breakthrough, this advance in our understanding of nature, we actually progressed forward. This is why physics is so important. I can tell you right now, your life will not change one instant from the moment that you're young to the moment that you're old unless our understanding of physics changes. Our understanding of physics hasn't really advanced very much in the last 50 to 70 years. Hence, all the technologies that you're seeing are just applications of physics that was already known. Einstein and others came up with the concept of the laser in the 20s and 30s. The laser wasn't actually realized as a practical device until like the 60s or 70s. Gravitational waves were thought of in the 1920s by the Einstein field equations. They were just detected by LIGO like 5 years ago. That's how powerful theoretical physics can be in situations like this. We can actually discover things that are otherwise hidden from us. And they would always be hidden from us if we didn't use this mathematical reasoning. That's the magic of physics and the power of physics. Most powerful subject ever. Okay, so now we're in a position to wrap up in a single package all of the relationships between electric and magnetic fields and their sources. And we've got 4 equations called Maxwell's equations. Maxwell did not discover these equations, but they're named after him because people are so impressed with this displacement current and how he figured out what the displacement current was that they named him after him, because he unified them. And actually there were 20 equations, and Oliver Heaviside unified them further into 4 equations, and he usually gets totally left out of the discussion. He gets screwed by the greediness of the historical tale. But he did a lot too to advance these. The equations that you see, Maxwell's equations, they are given by this. We have Gauss's law for electric fields. We have an integral of E or B over a closed surface. This is Gauss's law for electric fields, and we have Gauss's law for magnetic fields. The closed path integral of B dot dA is equal to 0. Why is that? Because there's no monopoles for magnetic fields. I put that on your exam as a challenge question, right? We can't have magnetic charge always has two, north and south. So any flux through a surface, a closed surface, is always going to be 0. And conversely, the line integral of B dot dA is always going to be 0 because of that same fact. Now, we also have that, among other things, magnetic monopoles, just like I said. There's a third and fourth equation that involve a line integral of E or B around a closed path. Now, these equations look pretty simple, but think about how complicated this is. On one side, you have an integral, and on the other side, you have a differential. These are nasty differential equations to solve in certain cases. This is not a simple operation. Figuring out these relationships for these fields and everything else, it's easy now, but it took people 20 or 30 years of intense study every day to get it in that form. Heaviside worked on it for decades. Okay? And then, so the third and fourth equations involve a line integral of E or B around a closed path. Faraday's law states that a changing magnetic flux acts as a source of electric field. We saw it here with the displacement current. Now we're seeing it in its final form. The negative of the time rate of change of magnetic flux through a path equals the line integral of the electric field around the path. Thus, a changing magnetic flux is a source of electric field, and there is a changing magnetic field which must be carried out over a stationary closed path, and it's not 0. Thus, the E field produced by a changing B is not conservative. That's the reason for that. So the fourth and final equation is Ampere's law, including the displacement current. So now we actually take this displacement current, and not only do we infer that it exists, we actually put it in the actual equation, even though you can't really measure it with a galvanometer or whatever. Actually, you can sort of with the if you measure the magnetic field, but it's not like a current in the normal sense. Okay, so this equation, Ampere's law, states that both a conduction current and a changing electric flux act as sources of a magnetic field. So there's a lot going on here. We've got a line integral of a magnetic field around a path. We've got a magnetic constant here. We've got our current. There's a conduction current, and then there's this displacement current that's expressed in terms of the change in electric flux. So we don't write little ID there because we still don't like that. We're like, it's imaginary, we can't measure the current, but we can measure the change in flux. So instead of writing the law in terms of the displacement current, we take the displacement current expression and we write it for the change in the electric flux. But that is the displacement current through the path. It is. That's where that comes from. It never would have been discovered without that theoretical device, that thought experiment by Maxwell. And Einstein, this is who Einstein was like always looking up to when he was doing his work. He was a massive fan of Maxwell. That was his, like, Maxwell and Faraday both. But he had like pictures of him always in his office because he was so impressed by this thought experiment that Maxwell did with the displacement current. It inspired him to do his own thought experiments and imagine situations that seem silly and impossible, but maybe they could be useful for mathematical ideas, and they were. So we can look at the electric field and its role in Maxwell's equations. In general, the total E field at a point in space can be the superposition of the electrostatic field caused by the distributions of charges at rest. So we have an electrostatic field and a magnetically induced non-electrostatic field. So the magnetically induced electric field is non-electrostatic, and that's the total E field. The E field is that due to the charges and to the induced electrostatic field from the B field, inducing an electric field. The electrostatic part is always conservative. Line integral of EC.dl is 0. This conservative part of the field does not contribute to the integral in Faraday's law, so we can take it out, and we can take the total electric field, including the part for EC due to the charges and the magnetically induced part. The non-conservative part of the field does not contribute to Gauss's law, because this part of the field is not caused by static charges. Gauss's law only applies to static charges. So hence, line integral of En dot dA is always 0. We conclude that in all of Maxwell's equations, E is the total electric field. These equations don't distinguish between what's conservative and what's non-conservative. They don't care whether it's a conservative or non-conservative. They just care about the total E field in general. So our principle of superposition for a vector field applies to the electric field. Whether it's electrostatic or not, the two fields combine linearly and obey linear superposition. Thus, they can participate in the same vector equation. That's critical. In order to write vector equations for fields, we have to obey the principle of linear superposition. That's a basic concept for vectors that has to apply, and we have that. So there's a symmetry in these equations. In empty space where there's no charge, the first two equations are identical in form, one containing E and the other containing B. Those are just Gauss's law for electricity and Gauss's law for magnetic fields. When we compare the second two equations, there's a changing magnetic flux that creates an electric field, and the other one says that a changing electric flux creates a magnetic field. So in empty space where there is no conduction current, the two equations have the same form apart from a numerical constant, with the roles of E and B exchanged. So in empty space, there's no charges, so there's no charges at all. But look, we still have currents, well, not currents, we still have fields, even in empty space. Now this is the abstract part where we're really jumping into like the next level thinking here. So now Maxwell really gets ahead of himself and says, wait a second, we've got this situation. What about in free space? What do these equations tell me in free space? Well, in free space, I still have this change, this E dot dl is this change in B field, and then I have this B dot dl is this change in E field. Look at the symmetry there. The derivatives, they're only separated by a sign. So in empty space, there are no conduction currents, so the line integrals around any closed paths are related to the rate of change of flux of the other fields. And we can write these in a different but equivalent form by introducing magnetic flux as B dot dA and electric flux as E dot dA respectively. And then in empty space where there's no charge or conduction current, IC equals 0, Q enclosed equals 0, and then we have this form, the integral form of these equations. So now we have an integral, and look, they're looking even more symmetric. E dot dl is the integral of that is equal to minus d by dt of the total integral of the area, B dot dA, the dot product between B and the area vector. Same thing for electric field. The B dot dl is the dot product between E and the area vector associated with that, the time rate of change of the integral. So yeah, that's something you don't see in basic calculus, a derivative of an integral. Okay, that's a little bit interesting, but you need it for physics. Nature gets that complicated. So there's a symmetry there. There's a time-varying field of either kind produces a field of the other kind in neighboring regions of space. Maxwell recognized these relationships, and he thought, okay, I've got this B field changing that produces an E field, but then I have an E field changing that produces a B field. And he basically figured out, hey, that's light. Light is this changing field. And so that's what it is. These electric disturbances, electromagnetic disturbances, are time-varying electric and magnetic fields that propagate from one region of space to the other, even if no matter is present in the intervening space. And these disturbances are caused by electromagnetic waves, and they provide the basis for light, radio, and television waves, and X-rays. So there we go. We have light coming about, because even in where there's no charges, we still have fields. And if we have a changing, oscillating E field, that produces a B field. But that B field changes in proportion to it and reinduces the electric field. Now, light in actuality is a bit more complicated than this. This is only one aspect of light. This is the wave aspect of light. Light also has a particle aspect. In reality, light is neither a wave nor a particle. Light is a fundamental gauge boson field for the electromagnetic force. Okay? That's what it actually is. But in this class, we're just going to talk about the classical wave-like properties of it. And for a long time, because water has to propagate through a medium, the water wave, the height above the surface that the wave travels, has a medium, the water itself. So the wave, if we just look at the wave, that's the change in the height or the field. If the water wave is a field, you could say, okay, that's going to be my wave, and then my medium is water. They thought that there was a medium called an ether, and then Einstein came along and said, hey, you know what? I don't think there actually is one, and that explains some things. But we're getting ahead of ourselves, so I won't go into any more detail about that for the time being. But just know that now we can add an equation for the force due to a electric and magnetic thing. And this is the Lorentz force law. So the force on a charge due to electric and magnetic fields is F is equal to QE plus QV cross B. So all we did here was we took our classic equation for the force felt by a charge from an electric field and combined it with a magnetic field. That was actually in the first chapter, but I didn't put it on your exam because we didn't talk about electric fields. But now it's fair game because we talked about electric fields again. Okay, so we have the fundamental relationships of electromagnetism. Maxwell's equations would have even greater symmetry between the E and B fields if magnetic charges, magnetic monopoles existed. The right side would contain the total magnetic charge enclosed by the surface, and the right side of the other equation would include magnetic monopole current terms, but no magnetic monopoles have ever been found. And in conciseness and generality, Maxwell's equations are in the same league with Newton's laws of motion. This is, yes, they're absolutely very important, and this was a major achievement. So, that's all we're going to have to say about Maxwell's equations. There's a symmetry. Electric fields, changing electric fields induce magnetic fields. Changing magnetic fields induce electric fields. And the two work together to produce propagating light. Now we're going to talk about inductance. Inductance this is the next chapter. Just a little segue into the next chapter here. Inductance is this property where a coil of a wire behaves differently in a circuit than the same wire that is straight. So coils we have like a coil of a solenoid or something. I won't bother to draw it out, but we can just think about it for now. They increase the voltage for a circuit. So a 12-volt car battery can give thousands of volts to the spark plugs. So how does this work? It works through inductance. A change in current in a coil induces an EMF in the adjacent coil. It goes right along with Maxwell's equations. The coupling between the coils is described by their mutual inductance. So a change in current in a coil also induces an EMF in that same coil. And this is an inductor with a self-inductance. If a coil is carrying a current and that current decreases, energy is released while it decreases. So we have two concepts with inductance in circuits. We've got self-inductance of the inductor by itself, and we have mutual inductance of two inductors in some kind of a circuit. So mutual inductance. A change in current in a coil induces an EMF in the adjacent coil. The coupling between the coils is described by their mutual inductance. A change in current in the coil also induces an EMF in that same coil. And these coils are called inductors. And the relationship of current is described by inductance, also called the self-inductance of the coil. If the coil is initially carrying a current, energy is released when the current decreases. This principle is used in ignition systems, and we find that this released energy that was stored in the magnetic field caused by the current that was initially in the coil. So this is fascinating. So we have this inductance property where we have the magnetic field actually stores energy. Okay, how does magnetic field store energy? If you take some air track gliders and you take them and you put magnets on them, you'll notice that the magnetic field can push the other one away. And we can take kinetic energy, right? We can take two air track gliders. I should just try to get one of these set up in this classroom, because this would be useful. They both have magnets, right? Like north, south, and we put them on some track, and they're going towards each other. What happens is, if I push both of these magnets, they have some kind of energy, 1/2 mv squared, right? 1/2 mv squared. They're both coming at the opposite direction with some kinetic energy. The kinetic energy is a scalar because the velocity is just a scalar, it's squared, so it doesn't matter. One of them's going this way, one of them's going this way. What happens when these two magnets come together? The magnetic field causes a repulsion that instantaneously brings these things to a stop, and then they split back apart again. So what happens is kinetic energy must have been converted into magnetic field energy and then given back to the air track gliders. So there's another fundamental relationship between a mechanical system where we initially give two air track gliders some sort of push with our force, and then that energy that we use with our hands is converted into a magnetic field energy. The magnetic fields take our energy, store it for a minute, and then release it. Inductance is kind of the same sort of idea, except with a circuit and with currents. So that's sort of like some physical intuition for how magnetic fields can store energy. You can see how they can take kinetic energy and store it as magnetic potential energy, kind of like a spring. And that's what you'll see. The same analogy. They make an analogy between these magnetic inductors and springs, because if these were two springs, the springs could compress and bounce off of each other in the same way, right? So the magnetic fields work a lot like a spring, and that's also why electric and magnetic fields quantum mechanically are treated as simple harmonic oscillators. You'll see in quantum field theory, the first thing you do is you try to write a simple harmonic oscillator as a quantized field. That's why, because electric and magnetic fields act like simple harmonic oscillators, except in a field throughout all of space, rather than like an actual spring. Anyway, that's enough for today. We'll talk more about how inductance works in circuits next time. Have a great Halloween.